Hello everyone, my name is Thompson Miner and I'll be presenting some of the findings that I got during the Lab 3 circuits. Introduction. Some of the key ideas we'll need to know will be the circuit rules, the loop rule and the node rule, Ohm's law, energy conservation and charge conservation, resistors, batteries, ammeters, voltmeters, parallel and series circuits, resistors, which are the resistor capacitors, the resistor capacitor circuits, and time dependence. These are some of the laws and rules that we will require to know for the lab that we're about to conduct today. As you can see from the setup, this was the setup, and there was two ammeters that were connected with which were both read 0.024 amperes because they were in series. They both received the same amount of current. When one of the ammeters was replaced to be a voltmeter, the current in reading from the ammeter did not change, stayed the same. But since it was a voltmeter now, it had a reading of 3 volts in the circuit. When the circuit was closed, the change in voltage across the battery was recorded to be negative 2.6 volts. And the change in voltage across the 100 ohm resistor was recorded to be 1.7 volts, while the change in voltage across the 47 ohm resistor was recorded to be 0.7 volts. Change in voltage across the ammeter was recorded to be this. The sum of these change in voltages was recorded to be negative 0.12 volts, which is supposed to be 0 volts, but since we neglected the presence of resistance across the wire, that is why our results were not ideal. And then this is the graph of the voltage as it traveled across the circuit. As you can see, the voltage rises across the battery and then stays the same, but once it goes across this resistor, it's supposed to go down and then stay the same, and then next one, another resistor go down up until it eventually hits 0. Observations and questions. Question like, why doesn't the addition of the voltmeter change the ammeter reading? The voltmeter has a very high resistance and therefore very little current flows through it. Thus, the ammeter does not detect any change of current in the circuit. What happens if an ammeter is connected in parallel with the 100 ohm resistor? Both ammeters will read 17.9 milliamperes. Resistance of different circuit elements. The resistance is calculated, the change in voltage divided by the current. So across the 47 ohm resistor was 35, across the 100 ohm resistor is 85. This was due to some of the things that we neglected, such as the resistance across the current. That is why the values here are not the same as the values that the resistors were actually made for. The resistance across the wires and the ammeters, we neglected them and found them to be 0. When it comes to the part B, RC circuits, what happens to a bulb when a battery is connected to a series RC circuit? The bulb becomes very bright and then slowly dims until it is off. With the 8.3 ohm resistor, it takes 12.7 seconds. With the 33 ohm resistor, it takes 58.8 seconds. And what happens when the battery is disconnected from the circuit? The bulb becomes very bright, then slowly dims until it is off. With the 8.3 ohm resistor taking it 9.1 seconds, with 33 ohm resistor taking it 49 seconds. This is because the bulb gets bright while the capacitor is charging, but once it is fully charged, it starts dimming off. And then over here, once the battery is disconnected, the current starts flowing again while the capacitor is discharging. And then finally, once the capacitor is completely discharged, the bulb turns off. So what if you charge the capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? The capacitor will get charged instantly because there is no resistance. How quickly the capacitor charges is dependent on the amount of resistance in the system. Would the prediction happen in real life? No. This is because in real life there's a lot of resistance from wires carrying the current combined with the resistance in the batteries themselves.